Hi guys, welcome back. In this video, yes, I think it's time to do some more challenges of the microcorruption. I know it's been a long time since I posted a video. I was having exams. Yeah, I just finished them now. Anyway, guys, so basically the previous challenges we have solved tutorial, we have solved New Orleans, and we have solved Vancouver. Now here's the following plan for today. So the goal is that you try to solve them on your own. You try to solve the challenges, for example, Sydney and Baku on your own. We'll be trying to solve, for example, in this video, 3 challenges. So the idea is that you will be solving on your side, and if you get stuck, just come back to the video. Otherwise, just come back anyways. You can just watch it. Watch it, and you might just notice something new if you have solved it, or I don't know, just you can just see the solution that I will be trying. I will be trying also to explain some stuff aside from the challenges. So yeah, so let's start with Sydney. So what do we have? So the same message that we always, let me just zoom a little. Yeah, like that, it's good. Yeah, so let's just run that and see what's gonna be given us. So it's given us enter the password to continue. Um, this is a pretty common challenge that we already encountered in microcorruption where we have to give a password. For example, let's just give some random. Mm, so what do we have? It's not doing a thing, and it's quitting. Okay, let's reset. Let me just move a little back. Let's reset. Freeze, reset that, and we continue again. It's gonna be giving us the same thing. So let's just take this code. Um, and try to analyze it statically. So what do we have in here? So yeah, so let's search for the main. So what do we have? So we have the main. So the first line is the one of the usual lines that we have. So it's just some stack alignment. Usual line. Stack preparation. Preparation. Or just prep. Stack prep. Yeah. Then he's moving the string into the password to continue into the register 15. This is a pretty common thing. He's preparing to call the puts, which is the calling of a function, and as we saw in the previous videos in the introduction, we already have introduced the architecture of the MSP 340 that the code will be working on, or that the code will be executing on. And as we have so in the data sheet, the register 15 is used to pass on the parameters to the functions or the arguments to the functions. This is just some argument, and this is basically calling the puts function. We basically call that with a message, and this is the message. Then he's moving the stack pointer to the register 15. So register 15 should be equal to the stack pointer that is pointing to. So let's say, for example, let's just take a look and try to break into the main just to know the actual offset that he will be using. So we put a breakpoint there, and then we just continue. If we continue, let's just give, for example, I don't buy it, and then we hit C again. We did not hit the breakpoint. Wait a second, let me just reset. Yeah, we hit it. Now we hit the breakpoint. Okay, so what do we have? I want to know the offset of the stack pointer. So the stack pointer is at 439C, which is in the memory should be here. Yes, 439C. Yeah, it's this block. So I suppose if we send iron white, it should be here. Let's just do that. So it's gonna be 0x 439C as the offset of the stack pointer. Now he's gonna be calling get password. So calling get password with just the stack pointer as an argument. Then he's gonna be moving that password that we have that we have given to another function, which is the check password. So yeah, so I suppose it's gonna be the same offset since the get pass since the get password won't be changing the offset that we will be working on. So yeah, so I suppose we will be calling here, calling the check password, but it's gonna be called with the SP. Yeah. So and then it's gonna be testing if the register 15 is equals to 1 or if the register 15 is equals to 0, which is a pretty common thing too. Now what do we have? So we have a conditional jump that will be jumping if not 0 to the actual to the actual instruction that we are working on plus 0xc, which means that it's gonna be jumping to this value plus c. Let's try to check this value out. So we have hex of 0x plus 0xc, which is 445e, which is this instruction. Now let's just divide them together so that we can understand the blocks that we have. Um so this is if the resistor 15, um if it's not 0, it's gonna be jumping here. Otherwise, it's gonna be working here. So if the resistor 15 is equals to 0, it's gonna be giving us invalid password. Try again. Otherwise, he's gonna be this is, I suppose, the exit, jump to exit, or just exit program. You can just call it exit program if you want, guys. Yeah. And this is gonna be if the register 15 equals to 1. So the goal, guys, here is to pass down a password to the check password that we'll be checking on now, and the result of the check password should be equals to 1. So let's just try to find this function. So what do we have? So yeah, let's see. So it's comparing the 0x40 4E24 with this one, and then it's gonna be checking this one too. Okay. So let's try with this one. So it's comparing actually the values 0x4E24 with register 15, with what's in the register 15, with what's in the register 15 um, plus 0. And then if it is not equal to 0, then he's gonna be exiting the program again, or exiting the check password, I'm sorry. Else it's gonna be doing the same checks always and always again. As we can see, same checks are gonna be happening, except that we each time change the value of the value that we are checking. This is just setting register 14 equals to 1, and this should be another value. Now we have to change the values in here so that we can understand. Compare, compare, and we compare, except that we compare each time 2 bytes with 2 bytes. We compare them 2 bytes with 2 bytes. This is the thing. We also do another conversion at the end with the latest 2 bytes, which are this one. Yeah. So what do we have now? Um, what do we have? Yeah. So if they are equal, then we jump directly to the exit and we clear. So this will be jumping in here. So the idea is that we want the check password to return a 1. And if we check the register 15, we see that the result at the end of the register 15 will be the same result as the register 14. But the thing is that he's gonna be setting one if all those checks are well. He's gonna be moving one into the register 14. And then if the latest two bytes are cool, are I mean I mean when we compare them together they are the same, then we can just finally just move the register 14 into the register 15 and then return a 1. But if, for example, this check has failed, then he's gonna be clearing the register 14 and just put a 0 into the register 15 and then return to the main, which will be returning obviously E0 instead of a 1, and we obviously get an invalid password. So the idea is that we should just send him an input that has those bytes. Now the trick in this challenge is that, for example, let's just try to send them like that. Let's try to build them together. Let's just try to get them as they are without any changement. Let's just do that and see what we will be getting. So if we send him this payload, so for example, let's say we're gonna be resetting. Um, let's try if we can unlock the door using that. So we will be checking to send a hex encoded input, and then we send that. And as we can see, we have jumped to the end of the program without having access to the door. So let's try to set a breakpoint um, just to see the values that are in the register 15, for example, when he's gonna be comparing that, just to see them out. um, so let's reset, let's continue again, let's send them those values, then let's send them out. Now let's continue, and then we hit the breakpoint. Now let's try to see the address. So it's 439C for the register 15. Let's try to see the values that we have sent. 439C, 439C. So yeah, here's my values. But there is just one thing that, for example, we have sent um, we have sent 4E 24 54 6B 29. You see, we have sent those bytes, but there is a trick. There is something in this in those bytes that we have sent is that they are somehow they are somehow flipped. And the thing is that if we want to, for example, if we want, for example, to compare them with the values that are in here, we are actually having a problem. We're actually having a real problem. Well, the problem is let's try to step in to see what is the problem exactly. So he is gonna be comparing that together. So the state U register is giving us a negative, which is a 4, which means they are not the same. Oh, well, the problem is he's gonna the state U register sent as E and N which means that they are not equal when actually they are equal. Well, the thing is that it comes out that the comparison when it comes to comparing 2 bytes with 2 bytes, especially hard-coded bytes, um, the the Indianness matter. Now, what is the thing about Indianness, guys? We actually, I don't know if I have explained before the little Indian or the biggest or the big Indian, I'm sorry, in my videos, but I suppose in these series of the reverse engineering, if you check them out, I have explained them pretty well. So the idea here is just to reverse the bytes in each one of them. So how to do that? We just have to reverse the bytes in order to let them um, let them be compared. So 25, 76. And then let's try this out. Let's try to see this reset. C, and as you can see, we have the door unlocked. So the idea was this: you should just simply have to flip the bytes in the hard-coded values that you have. Well, we do that simply because the conversion that happens when you try to execute this code is that it takes the values in the little endian. Instead of just comparing from left to right, it compares them from right to left. This is obviously the trick about this Sydney challenge that you have just so in front of you now. Well, it's an easy challenge. I cannot see like something new, to be honest, but yeah, it's a pretty easy one. Yeah, let's just move on to another one. Um, I think we didn't just validate that. Um, we can, I suppose, solve. Yeah. Yes, let's go. We have solved that. Let's go to Hanoi. Hanoi, have a 20 points too. Had a 20 points on it. Yeah, what do we have? Oh, I think this is a bigger one to check. So let's just continue and see. Enter the password to continue. Remember, passwords are between 8 and 16 characters. Since they are between 16, 1, 2, 3, 4, 5, A, B, C, D, E, F. Is that cool? We can just add a 0, for example. What do we have? So it's exiting the program, obviously. So let's try to read the code. Let's try to get all of that and read it. What is the main? Here's the main. So the main is calling a login function, which I suppose we should know, and then is clearing the register 15. So if we take a look at the login, it is a function. So what do we have? So he's moving E0 to um, to the address 0x2410. Then he's usually doing the same stuff, just calling the enter password, calls the puts, and then he's moving 0x1c into the register 14, and then he's moving that address to the register 50. I suppose the get string is gonna be getting the size of the string that we will be given, and the address where the string will be written. Yeah. So this is the size. So this is the size, and this is the place where we will be writing the input. Let's just say the address. Address is good. Then he's moving the string that we have gave. He's gonna be passing that to the register 15. Then he's gonna be calling a function to check the password again. Test password valid. So if then he's gonna be obviously testing with the register 15. Then if it is E0, he's gonna be obviously jumping to the current address plus 0x8, which gonna be pretty sure this gonna be, it's either gonna be this, I think. If we add an 8 to this, yes, it's supposed to be that, yeah. So if the register 15 is equal to 0, then we're gonna be moving on to testing if the password is valid. So yes, yes, he's gonna be printing for us, testing if the password is valid. Did we show that later on? I don't remember. We didn't see that message when we tried out. But anyway, then he's gonna be comparing one byte at the address 0x2410 with the byte 0x99. Then he's gonna be jumping if it's not equal to 0 into this address. Otherwise, he's gonna be having access granted. So I suppose he's just checking if this byte is set to 0x99, which is the offset. So if we just check the offset of this address with the address of the input, we see that there are 16 bytes between this address and this address. You can just subtract them together, you will get 0x10, which is 16 and decimal. Um, so yeah, so if we send some random bits or random byte, I suppose, or random bytes, or I don't know exactly, we have to check if there is some specific pattern in the password that should be valid to obviously validate it. If there is any specific pattern, then we might just have another thing. But otherwise, I think if this byte is set, then we get the access granted. So this byte should be set. Yeah. Now let's go and check the test password valid. Yeah. So what do we have? So we are gonna be pushing the register 4, then moving the stack pointer to the register 4, then incrementing the register 4 with 2. Just fun fact, guys, this is gonna be incrementing the register 4 with 2. It's just like doing, for example, register 4 equals to register 4 plus 2. And decrementing the stack pointer is just doing stack pointer minus 2. With the D, obviously just makes sense of doing it too. You can just check that on Google if you want, or you can check the data sheet of the MSP 430 to know more about that. So then he's gonna be moving 0 into register 4. Register 4. Actually, he's gonna be putting 0 to the address pointed by register 4 minus 0x4. Um, he's gonna be giving 0, obviously, yeah. Now next he's gonna be also register 14. Now he's gonna be setting 0xFFC. Then register 14 equals to register 14 plus register 4, which is equal to um, this address plus what's in the register 4, which we have to know dynamically. Then he's gonna be pushing just one fact, guys, that I missed here. Stack pointer is gonna be shrinking back um, when we do that, obviously, and register 4 should be equals to the stack pointer. That we should know the value obviously dynamically too. Then he's gonna be pushing those values. The stack pointer is gonna be shrinking to another value, which is obviously the number of the interrupt that he will be calling. And then he's gonna be moving another just one byte from this address or from this offset into the register 15. Then he's gonna be signed extension, so the SXT is just doing some extensions to the register 15. I think the best way to debug this code is just to run it dynamically. Just set a breakpoint and see what is happening. It's better, I think, to do that. So what do we have? So let's just set a breakpoint there. Let's reset. Let's go. And this is saying, for example, 1, 2, 3, 4, 5, 6, 7, 8, C, D, E, F. Just let me do something. I want to check something out, but let me just for now try to see how this test password is working exactly. So let's go. So we hit the breakpoint. So let's try to step, and we want to track the value of the register 15. What is the value that we want from the register 15? Let's just go back. So we want the register 15 to be 0. Yeah. So let's see if this value is gonna be changed. Yeah. So here's in the interrupt. Let's finish. So the good thing now, for now, the register 15 is 0, which is a good thing. Now if we continue, it's still 0. That's a good thing. Now he's just disallocating the stuff that he allocated using this instruction for the stack pointer or for the stack, obviously, and he's pooping the register that he have pushed, and then he returns. So obviously, just giving some random input, the register 15 is obviously E0. So then I suppose next he's gonna be just going in to jump to the login, obviously because it's a 0. As you can see, have jumped this instruction that can actually change the value of the uh, of the of the offset of the byte that we have talked about that should be set in order to get the grant access. And then now he is moving on to testing if the password is valid. Obviously, put um, we didn't put actually the byte 0x99 on that offset. If we can just go and check that out. So 2410. Let's go to this offset and see. So yes, I didn't set that out. Obviously, I didn't do that. So yeah, let me just reset and try to set it out. We can just, for example, craft an input for that too. Let's say, for example, we're gonna be sending. We can just do that in Python. It's pretty simple way. Let's suppose I want to have payload equals just a simple AES by 16 just to fill the first ones plus um, obviously bytes plus a byte that is 0x is obviously 0x99. It should be just the hex of that. Okay, let's just do bytes from hex because I don't know exactly the byte for that. Just let me check if the number of the byte is right. Yeah, it's 0x99. Yeah, cool. Let's just print that out. Yeah, it's cool. Now I wanted to encode that. We obviously cannot do that because the object has payload. Yeah, it's already encoded. What am I doing? I want to know the hexadecimal of that one. Just a second. Yeah, I remember that. It's E4841. Suppose it's B41. We don't need that too. This is print the payload for me, and yes, I can just add that manually. Let's go back. What is the microcorruption? Maybe I99. Let's now send that. Yes, we have solved it. So the door is unlocked. Yes, so this is another pretty easy challenge, guys, to be honest. It doesn't take too much time to just figure that out. Let's just solve that. Move on to the next one. Sorry about that. I forgot about the my 99. Yeah, cool. Now let's try to solve Baku. Yeah, so this is gonna be the last challenge for this video. Um, yes. So let's try to see. So it's scanning for security device. Um, so it's a scanning. So let's see what is scanning exactly. What is scanning exactly? So yeah, we send that. See, to continue. It's keeping on scanning. That means that it doesn't actually accept the input that we have sent, but there is a lot of code to be honest. Just to check out. What is this thing? What is this thing? Yeah. Let me just search for the main. Yeah, so this is the main. So as always, some stack alignment. Then he is gonna be moving 10 to the register 13, then clearing the register 14. Then he's gonna be passing the stack pointer to the register 15. Now we have three arguments passed to the function memset, which gonna be setting the memory to a certain value. The value should be what's in the register 14, and the address to be set is gonna be pointing to by the register 15, and the register 13 should be having um, the size of the buffer that we want to set. So it's gonna be 16. So we're just setting 16 bytes or 16 zeros pointed to by the stack pointer. Then he's gonna be printing the scan security device. Then he's gonna be moving 16 to the register 14. Then he's gonna be moving what's in the stack pointer to the register 15. Then he's obviously gonna be reading something. So he will be reading 16 bytes using this code or using this bunch of lines. Now, what do we have? So register 14 should be equal to our input. This is so he's moving some string into the register 15, then he's calling IES ECB decrypt. Okay, so there is some crypto into in this challenge, so it's something new in the microcorruption. We didn't encounter something that has to deal with cryptography, so it's time I think to just explain for you um, what this what IES is exactly, just for you to understand the thing before we start solving the challenge. Yeah. So we basically have encryptions in cryptography and in security in general. So there are two types of encryption that we can have. So for example, we can have symmetric encryption, symmetric encryption, and we can have also asymmetric encryption. Well, what is the difference exactly between symmetric encryption and asymmetric encryption? In symmetric encryption, we usually have something um, called a key. So you usually give your message, um, and you give the key, and let's call this, for example, a function that's gonna be doing some encryption. Let's just call it E, and then the E should be giving you something called E cipher. In symmetric encryption, guys, we usually use the same key for encryption and decryption. So, for example, when you have a message that is encrypted using a key that gives you a cipher, so if you give the cipher and the key to the function that will be decrypting, it will be giving you your message back. So that's why we call it symmetric encryption. This is why we call it symmetric, because we obviously use the same key for encryption and decryption. Now, for the asymmetric encryption, we have two things. One called a public key, which we always denote it as an E, and we also have a private key, which we denote it as a D. So the E or the public key is used for encryption, and we usually use the D, which is called the private key, to decrypt the message or for decryption. So that's why they always tell you you should protect your private key, or you don't have to give your private key to people because they can decrypt the data, and that's why you usually find the public keys everywhere on the internet. Yeah. This is for the symmetric and the asymmetric encryption. So yes, so what do we have next? The thing is now about IES is that IES is a symmetric encryption, and it has a bunch of modes that is operating on. So the IES, for example, we have a mode that is, for example, on this challenge we use the ECB mode. So the ECB mode, or the electronic code book, is basically a cipher block encryption. So basically, you have your message. Let's suppose, for example, you have a message. Let's say, I don't know, for example, hello. Basically, to send, for example, or to encrypt this message using the AES ECB mode, you usually, and you obviously should be having a key, and you should divide your message into blocks. Now, the size of the blocks depends on the mode used and on the size of the key itself. So, for example, if the key size is 128 bit, then you should be dividing your blocks into 16 bytes. If your key size is 256 bit, then you should divide it into 32 bytes blocks. Blocks of data. Now the thing about IES, guys, when we talk about the ECB mode, when you have a lot of blocks, you obviously divide your message into blocks, and each time to encrypt your message, you usually give the block 1, for example, block 2, and block 3 just after you divide your message into blocks, and you give the same key that you have provided when you wanted to encrypt, and it's gonna be encrypting all the blocks with the same key. This is why they usually don't recommend using the IS with the ECB mode, because it's vulnerable to a lot of attacks actually. One of them is called the Oracle padding. You can check that. You can, for example, just Oracle padding attack. It's pretty common thing. It's pretty common attack actually, where we attack the IES ciphertext using that. You can just check that out if you want. So this is basically how the ECB is working. There is a lot of other modes. For example, there is the CBC, the chain block cipher, which came to improve the EBC and, let's just say, mitigate some of the vulnerabilities that are pretty these are pretty common with the EBC. We usually just did a little enhancement to the EBC just by trying to just add an initialization vector, for example. In here we call it IV, and you just XOR that with the block 1, for example, and the result of this block XORed will be XORed with the block 2, and you actually do that with the other one too. So this is for the CBC, the chain block cipher mode for the IES. Yeah, but for now, for our challenge, we will be dealing with the ECB, which is a pretty simple one. So, as we have seen now, I suppose this is gonna be the key, since he's passing on the input and he's passing on the key. So this is the input and this is the key, and now he's gonna be calling the IES decrypt. Once he decrypted that, he's gonna be setting 16 to the register 13. Then he's gonna be moving the input that is in the register 14, and then he's gonna be comparing that with using memory copy with the access granted. So I suppose the IEC ECB decrypt is gonna be decrypting our input and setting the decrypted version into the stack at the offset that is pointed to by the stack pointer, and then he's moving on the value to the register 14, I'm sorry, and then just he's just gonna be comparing the register 14 with the register 15. Yeah. So how can we solve such a thing? We should be just taking a look at the IES ECB decrypt. What is doing exactly? So there is a lot of thing, and as we can see, since it's ECB, this obviously we will be having a lot of blocks that will be decrypted just using this function. But let's just make a thing. Just let's try to see what this code is doing. So he's pushing the resistor 11 and resistor 10. Then he is moving into the resistor 10, the resistor 15, which contains the access granted, I suppose. Is it the access granted? Oh no, it's not the access point, it's the key actually. Yeah. Then he is gonna be doing register 11 equals to register 14, which um is gonna be the input. Then he's gonna be register 15 equals to register 14, which is the key, obviously. Or I have inversed them. Sorry for that. Yeah. So register 14 should be that, and register 15 should be equal to register 11, which is the input. Now he's calling the XOR 128, so that means that he will be getting a 16 bytes and he will be XORing two 16 bytes together. So if, for example, if we send him a 16 byte value, he will be XORing the input with the key and then gets the result back, obviously, into the register 14. We can check that out. For example, let's try dynamically to do that and check if the assumption that we have set is true or not. Let's just go into the AES decryption. So this is the main. This is the boot sticks time AES decrypt. Um, yes, let's try to see the result in here. So if we go and we continue, let's say for example we want to send. Let's try to do that manually. Just check that with the code. For example, um, let's say it's a plain. Since we will be decrypting ciphering, say cipher get random uh, bytes 16. What else do we have to do? We print the cipher, obviously, and we have to also get the key. We also have to get the key. So to get the keys, I suppose we can just download the binary and just open it up in a software called HXD. It's a helpful software tool, guys. You can just use it. It's a pretty good tool, to be honest. It helps me whenever I do some hexadecimal or hex stamp analysis or in any kind of binary, just to see the hex of it, and it gives you the rows. So you don't have to to search pretty much a lot of that. Yes, so we are now there, I suppose. Nope, we didn't yet, but I want to know the address of that. So I want to first just know the address of the key. So I want to just yeah. So since we have said that the key is gonna be the register 14, if we take a look, so this address, now let's check that out. Let's just jump there. So it's since the key is 16 bytes, it should be this one. It should be this is the key. Now if we take that, key equals to that. Um, this is the key. Yeah. So bytes from hex. So this is the key. Now, if we just let me just print the cipher as a cipher just to understand that, and then we print string XOR of the cipher and the key. So yeah. So let's just hexify that directly. That hex. Yeah. Cipher dot hex to So if we go and we send that back to the, should be given us something there. So we want to see the result of the XOR if it's the same or not. So if we take a look at the address, the address, not the key now, we want to see the address of the input if it's gonna be, if the result is gonna be there or not. Yeah, so it's gonna be the register 15, which is this address. So let's just check that out. 4400. Yes, this one. Let me just check that out. Oh no, it's the stack pointer. I'm sorry about that. It's the stack pointer, yeah. So yeah, this is the resulted, as you can see, 96 3F 107. Yeah. So yes, the assumption is true, and the result of the XOR is gonna be the same as the input. So if the input is that, and it's actually the R11, it's not the R15. Sorry about that. Yeah, it's 43F0, which is the same offset of the stack pointer. Um, yeah, so the result of the any of the operations will be the same as the input. Then he's gonna be doing another thing, which is moving the resistor 10 to the resistor 14, and as we can see, the resistor 10 is having the offset of the first key, and then he's adding E16 to the resistor 14 to get, for example, a new key. Let's just call it key 2. And then he's moving the offset of the resistor 11 to the resistor 15, which is the result, which means that he will be passing the result of the latest operation, which is the XOR, to the AES decrypt 128. So we only have one thing to conclude from these lines of code, which is that the key 2 should be also just below the 7F 78 75 key, which is this one. So this is the second key. So if we do the same with the other pattern, we should be having this is as the key 3, and this as the key 4, and this as the key 5, and this as the key 6, and this as the key and this as the key 7, and this as the key 8, and this as the key 9, and this as the key there's a lot of keys, to be honest, and this as the key 10, and this as the key 11. And then he's doing some substitutions and a lot of stuff that you can check on your own, to be honest. You can just check them out. He's doing actually a lot of operations on that. So each time, so he's getting the result, and then he's doing the key. So if we tried, for example, to just if we try, for example, just to um, how do we explain this? Just make a sketch of that. So he's doing just this. So you are giving a cipher, and then it's gonna be going on into an XOR with a key, with the key one, and obviously the result will be going on to into an IES decrypt with obviously a key 2, and the result will be going on into another IES decrypt, obviously, with a key 3. We do that until we get into the key 10, uh, and then we actually get that into another block, which is a substitution. Let's just call it a box, but this box key is actually um, has also a key, which is the key 11. Now the thing is, that should be giving you grant access, or access granted, or whatever it is. Access granted. Because he's actually, as we have seen in the main, he's gonna be comparing what's there with the access granted, which is this one. So you should be having access granted. You should be having access granted string. Yeah. How can we reverse that back? So we simply just get, well, basically this thing that I have did to solve this problem is just by using brute force, to be honest. Because at some point I have spent a lot of days with this challenge, but at the end I solved it somehow just using some brute force. How do you do that? I just simply try to decrypt, try to actually encrypt the access granted using the different keys that are in there. But obviously I didn't use the key 2 and the key 1. I tried to reverse back the processes by using the key 11 and then using the key 10 and then using the key 9 and so on. But somehow, just by trying to encrypt using the key 11 and then giving back the cipher was just the solution to the problem. So for example, to do that, we can just create a cipher instance just new, with a key, for example, equals to, the key should be the 11 one. So if we go into the hexadecimal dump, we see this is the 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is the 11th key. So it should be this one. So if you take this one, as a key, um, we can just do something like this to make the key, um, so bytes from hex. Okay, cool. Now the key should be that, and then we do is.mode. We give the mode, which is EBC or ECB. And then once we do that, we want to be encrypting plain text, which is access granted, I suppose. Yeah, it's access granted. Yeah, we want to be encrypting that. Yeah, so we can just print the encrypt or the encryption of that. So we call the cipher dot encrypt. Encrypt just did plain text. What is the problem? Data must be aligned with the block boundary in ECB mode. We should just add a 1 byte because it's 15, so yeah. We can just add that now by using that. What else we can do? Plus 1 byte of just a simple 0, I suppose. Just double zeros. Wait a second. We should be betting that. Gotta remember that. Let me just try to see IS, encrypt, ECB. Let's try to see, use something online. ABC online, encryption online, which is a better way to do this. So it's CBC, it's ECB, size, the encryption key, close. Close, please. I hate ads. Okay. My tools. Hex. Nope. Key. Hex. ECB, AES, plain text. It's gonna be access granted. Yeah, it's gonna be access granted. So I'm gonna encrypt that. Yes, so it's given us this one. Okay, if we try this out, it should be the one. Let's just try to do as always. Just make the payload in here. Payload equals to that. Let's just try this out. Yes, so this is the solution. So basically, guys, just if you take a look at this picture, I obviously at the first, well, to be honest with you, it took me a few days to solve this challenge. It wasn't that easy for me since I was just literally, you don't know any idea how much time I have spent on that. I literally reverse engineered even the IES decryption at some point because I thought it's doing something custom. It's not doing IES ECB, the implementation, the normal implementation. I thought it was a custom one, but at the end it wasn't a custom one. It was just me who just tried some some random guesses at the end just to check out the latest block. And I thought was the idea is that to just reverse back and get the cipher for this one, what I have to do is just encrypt the latest block or the access grant access or access granted with the key 11. That was the solution for me. Just to solve that, we can just use that. And yeah, let's go. We have solved Baku. Baku, by the way, is one of the few challenges in microcorruption that are not solved. I was really happy, to be honest, to solve it. It was a good one. I really enjoyed that. Good job from the authors. I love that. Yes, I think we hit the end of the video. Don't forget to subscribe if you haven't. Don't forget to follow me on Twitter too. Don't forget to join the Discord too. We have a family there. Yeah. Yes, I suppose we hit the end of the video. See ya in the next one. Bye.